Hey everyone, in this video we'll discuss the concept of heat of combustion with reference to Hess's law. Combustion is an exothermic reaction between a fuel and oxygen. Combustion reactions produce energy in the form of light and heat. Now, in the context of enthalpy change, combustion reactions are always exothermic because the enthalpy of formation of the products always is greater than the enthalpy of formation of its reactants. The reactants here refer to the fuel and obviously oxygen. There are two types of combustion reactions. Complete combustion occurs when there's sufficient or adequate amount of oxygen available for the fuel to react. In complete combustion, carbon dioxide and water are the products. Carbon dioxide is produced as a gas and water is usually produced as a liquid at standard conditions. Complete combustion is exothermic and usually produces the maximum amount of energy for a particular type of fuel. In contrast, incomplete combustion occurs when the oxygen supply is limited or when there's an inadequate amount of oxygen to react completely with the fuel. In incomplete combustion, carbon monoxide and solid carbon in the form of soot are produced instead of carbon dioxide. Now in real life, when there's an inadequate supply of oxygen, complete and incomplete combustion usually co-occur, producing carbon dioxide, water, as well as carbon monoxide and carbon in the form of soot. So even though incomplete combustion produces carbon monoxide and soot instead of carbon dioxide, usually we will see carbon dioxide produced as well, as there's always some degree of complete combustion, even if the oxygen supply is limited. As for enthalpy change, the one thing you need to keep in mind is that incomplete combustion produces less energy compared to complete combustion for the same type of fuel, because the enthalpy of formation of both carbon monoxide and soot are less than that of carbon dioxide. So in other words, in incomplete combustion, the formation of these alternative products releases lower amount of energy compared to the production of carbon dioxide in complete combustion. For example, methane, which is a formula of CH4, a carbon surrounded by 4 hydrogen atoms, is a common type of fuel that is found in natural gases. The complete combustion between methane and oxygen produces carbon dioxide and water. In the case where oxygen supply is limited, methane will again react with oxygen to produce carbon monoxide and water. The alternative product, in addition to carbon monoxide that can also be produced, will be carbon solid, in which case the stoichiometric ratio of the reaction will be slightly different. For the remaining part of the video, we'll be discussing enthalpy or heat of combustion using complete combustion as an example. When analyzing the heat of combustion or the enthalpy change of a reaction, we need to consider the enthalpy of formation of reactants as well as products, because the enthalpy change of that reaction is ultimately the difference between the sum of enthalpy of formation of the reactants and the sum of enthalpy of formation of the products. So let's take a look at combustion methane as an example. The enthalpy of formation of methane is represented by the following equation as well as the following enthalpy change value. Minus 75 kilojoules per mole, representing exactly 75 kilojoules of energy, is produced for every 1 mole of methane formed. Now, because methane is a reactant, we are not forming methane, but instead we are breaking methane into its constituent elements, carbon and hydrogen, then we are reusing this to form our products of combustion. So the enthalpy change involved in the combustion methane is actually the reverse of the enthalpy of formation of methane. That is, we are breaking methane or decomposing methane into its constituent elements, and therefore the enthalpy change should be positive kilojoules per mole for every methane molecule decomposed. This will be an endothermic process. Oxygen is the other reactant of combustion. The enthalpy of formation of oxygen is 0 kilojoules per mole because diatomic oxygen is already the standard state of the element oxygen. This value also indicates that if we are using oxygen as one of the reactants, breaking apart oxygen does not require any energy input, so the enthalpy change of this process would be 0. Let's look at the products of complete combustion of methane. The formation of carbon dioxide is represented by the reaction between carbon solid and diatomic oxygen gas, and the enthalpy change of formation of this reaction is minus 394 kilojoules per mole of CO2 produced. The formation of water is from hydrogen and oxygen gas, both of which are the standard states of the two elements respectively, and the formation of 1 mole of water produces 286 kilojoules of energy exactly. When carbon dioxide and water are being formed from the combustion of methane, this amount of energy will be produced, and this will ultimately contribute to the overall enthalpy of combustion, that is the heat of combustion. Let's look at this process in more detail in regard to the bonds and bond energies. We will begin with a molecule of methane. So I have a carbon atom surrounded by 4 smaller hydrogen atoms. The first process that happens is the breakage of the 4 carbon to hydrogen bonds to form the respective carbon and hydrogen elements in their standard states. And remember, this process is endothermic, which absorbs 75 kilojoules of energy per mole of methane. So we'll convert our hydrogen atoms into hydrogen gas, and the carbon atom will remain as it is. Now for oxygen gas, remember the enthalpy change related to oxygen gas will be 0, whether we are forming or decomposing it, because this is already in its standard states. So here we have oxygen, and the overall reaction for this first part will be the reaction between methane and oxygen to form our respective elements, oxygen, hydrogen, and carbon. Plus 75 kilojoules per mole is my enthalpy change for this first part. Now, the carbon atom and the oxygen atoms will react to form our first product, that is carbon dioxide. The formation of carbon dioxide will produce 394 kilojoules per mole of energy, and this can be added to the enthalpy change of the first process to give us an overall enthalpy change of the first two processes added together. When we combine the first two reactions, we have 2 molecules of oxygen on both sides, and we also produce 1 molecule of oxygen that's left unused in the reaction. The carbon atom that's produced in the first reaction is used as the reactant in the second reaction, so they can actually cancel each other out. This will give us a more simple final equation that represents the first two processes of this combustion reaction. So methane gas reacting with oxygen gas, producing 2 moles or 2 molecules of hydrogen gas and 1 molecule of carbon dioxide gas. The overall enthalpy is minus 319 kilojoules. This is from adding the two values together. Now this is not the end of the reaction, because remember, we still need to produce water. The hydrogen gas molecules will react with a further molecule of oxygen gas, and they will come together to form 1 molecule of water and 2 molecules of water. Remember that the enthalpy of formation of water was minus 286 kilojoules per mole of water. But this time I am forming 2 moles of water molecules, so I need to multiply this molar enthalpy change by 2 to give us a total value of minus 572 kilojoules. This is the third and final step of our combustion reaction. So by combining the 3 processes together, my final equation for this combustion reaction is the reaction between methane and oxygen gas producing a molecule of carbon dioxide and 2 molecules of water, liquid. The heat of combustion, that is the overall enthalpy of this reaction, would then be the enthalpy change of the previous 2 processes added on top to the enthalpy of formation of 2 moles of water. This gives me the final enthalpy change of minus 891 kilojoules. The detailed steps of breaking down the reactants and forming the bonds in the products can be summarized by this energy or enthalpy change diagram. The red arrow represents the formation of methane from its constituent elements, carbon and hydrogen. And we said that the enthalpy of formation of methane is minus 75 kilojoules per mole. The blue arrow represents the formation of carbon dioxide and water, which are the products of combustion reactions. The enthalpy of formation of carbon dioxide was minus 394 kilojoules per mole, and the enthalpy of formation of 2 moles of water molecules was minus 572 kilojoules. So when we combine the two, we'll get a total of minus 966 kilojoules. The formation of methane and the products CO2 and water can be derived from the same reactants, carbon, hydrogen, and oxygen. That's how they're related on this energy diagram. As for the complete combustion of methane, this involves the reaction between methane and oxygen gas to produce carbon dioxide and water. So you can see there are 2 alternative pathways of achieving the products of combustion. We either produce the products directly from the constituent elements, or we can react the elements to form methane first and then oxygen, which then undergoes a second reaction, and that is the combustion reaction, to form the same products, carbon dioxide and water. The combustion reaction and its enthalpy change is represented by the orange arrow and section of this diagram. This brings me to Hess's law and how it relates to the heat of combustion. Recall that Hess's law states the enthalpy change of a reaction is independent of the pathway taken, so whether it's a direct pathway or an indirect pathway composed of multiple stepwise reactions will be exactly the same as long as the starting conditions and the final conditions are the same between the two pathways. So this means the enthalpy change of the blue reaction, which is calculated here, should be equal to the total enthalpy change of the red reaction plus the orange reaction, which is combustion. That's why we can say the heat of combustion, that is the orange section of this diagram, is equal to the difference between the blue and red section. So we have the enthalpy change of the products, so of the CO2 and water, minus the enthalpy change of formation of the red part, which is the enthalpy change of formation of the reactants, methane and oxygen. And when we subtract the two, we'll get a final enthalpy change, and that is the heat of combustion of methane minus 891 kilojoules per mole. This represents the exothermic nature of this combustion reaction, and it's given in kilojoules per mole because it represents the exact amount of energy released for every 1 mole of methane that is used in combustion. The exact or total energy that's released can be determined if we know the quantity of fuel, that is in this example methane, that is burnt in combustion. This can be determined by simply multiplying our molar heat of combustion, this number here, by the number of moles of methane used in combustion. This will give us the energy Q released by the reaction. We'll talk about the use of this equation in further calculations in its own video. Let's look at an example calculation to consolidate what we've discussed in this video. Determine the molar heat of combustion of butane gas by using the enthalpy formation values provided in the table. Include a balanced chemical equation in your answer. So we'll start by writing a chemical equation, C4H10 gaseous, reacting with oxygen, and in complete combustion will produce two products, carbon dioxide gas and water liquid. The enthalpy of formation values of both products are also provided in the table, as you can see there. Now we need to balance the elements, so we've got 4 carbons on the left side, so I should add a 4 in front of the CO2. We also have 10 hydrogens on the left side, so we need to add a 5 in front of the water molecules to balance the hydrogens. Lastly, the number of oxygens is still imbalanced. We have 4 times by 2, which is 8. 8 plus 5 is 13, a total of 13 oxygens on the right side. So we should add 13 over 2 in front of the oxygen gas to balance the number of oxygens. This is the equation for the complete combustion of butane gas. To calculate the molar heat of combustion reactions, we need to remind ourselves that the enthalpy change of this reaction is equal to the sum of the enthalpy change of formation of the products minus the sum of enthalpy change of formation of the reactants. If you do not understand why this gives you the overall enthalpy change of the reaction, please refer to the enthalpy change diagram of methane that we showed and explained earlier. The products are CO2 and water, and we are given the enthalpy change values respectively. So let's start with the CO2. We have 4 moles of CO2, so 4 times by minus 394, plus 5 moles of water, 5 multiplied by minus 286 kilojoules per mole. That's the total for the products, and we'll minus the total for the reactants. And we have 1 mole of butane gas used in this reaction, so we'll just write down minus 127 times by 1. And again, for the enthalpy change of oxygen gas, this will be 0 because this is the standard state for oxygen already. So we'll add 0 here. This gives me a final answer of minus 2,879 kilojoules per mole of butane combusted. This concludes the video on Hess's law and heat of combustion. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.